My name is Benno, and the topic of my talk is high-performance computing, the toolbox for a physicist. I like to start my talk with a philosophical question about computing. Can a mathematician be substituted by a quantum computer? In a binary computer with the principle of the excluded third state, expressions are based on the logic that they are true or false. But what about this? This sentence is false. So if this sentence is false, it means it is right. If this sentence is true, so it means that it's false. So inside the logic, we cannot decide whether this sentence, this expression is true or false. And this is the proved theorem of Gödel's incompleteness theorem. The next question is the complexity of our brain sufficient enough to explain and understand the world? We like to have the understanding of the world, but we don't know whether our complexity of our brain is sufficient to do this. But we think it is, but there's no proof about that. Nevertheless, high-performance computing gives us the ability to find answers to questions which couldn't be treated in former times due to limitations in computing performance. High-performance computing is related to the following fields of investigations and opens new horizons of knowledge. We have it in quantum computing of qubits and supremacy, quantum cryptography and quantum information theory, neuronal networks and communication via cellular computers, fuzzy logic, machine learning, artificial intelligence, and in medicine with image recognition and more. These topics don't end. Everything is related somehow with computation. These are very interesting topics, but I have to limit the content of this talk to the fundamental tool for applications. So I will figure more on the question of the programming taking performance into account. So everybody knows Moore's law. Moore's law says that the number of transistors in microchips doubles every 2 years nearly. And this was invented by the International Technology Roadmap for Semiconductors. It serves somehow as a benchmark for industrial growing. So it is not a law in principle. It is somehow a benchmark where the industry would like to go. So it is not very convincing about a general lay. What I like to mention is that 1947 at the Bell Labs was the invention of the transistor by John Bodmann, Walter Brattain, and William Shockley. And now we have about 50 years of this international roadmap of growing. And it is somehow related to the increase of performance. Oops. So our technology of the computing is switching power dissipated by its CMOS devices. If you use the basic laws, the power is the voltage times the current. The current can be expressed as the charge times the frequency, and the charge is the capacitance times the voltage. So if we combine these laws, we end up that the power dissipated is proportional to the voltage squared or to the frequency. And this led to the consumption that the maximizing computational performance needs to be minimized in energy dissipation, maximized in operating switching speed, or of course the density, the maximum of the device density. But we enter on limits, which is somehow the power wall, because the dissipation of heat is in the order of, say, 100 watts per square centimeter. And the chip, the computation chip, has to get rid of this heat to guarantee functioning. So this is a limit of computation. Now, also, the frequency goes in the same direction. You cannot increase the frequency way too much, because you also adapt more heat to the chip. So the only thing to increase the performance is increase the density of the device. We have irreversible computing, which means every lost bit of information generates the amount of kT times the logarithms of 2 of heat dissipation in the computer. So the only way now to fulfill the roadmap of growth is to go for parallelism. And the law, the Amdahl's law, says how this parallelism depends with the speed up of a computation. So the famous law is given here. The speed up is the reciprocal of the serial part of the code plus the parallel part divided by the number of computing devices, n. So if we do a limit, for example, letting the system be purely parallel, so the serial part goes to 0, this means that p is 1, so the reciprocal of 1 divided by n is n. It is clear that the computation for a pure parallel application would scale with the number of cores, which does. On the other hand, if we do the limit of the number of computing cores to infinity, we see that the speed up depends reciprocal with the serial part of the computation. So the serial part of the program application limits somehow the speed up we can achieve. If we take, for instance, degree for parallelization of 90%, which is the yellow line over here, this means we have a serial code of 10%. And if we take, for example, 25 cores or 50 cores, we cannot increase the speed up. The speed up lies below 10 times the time of a computer. No? So on the other hand, if we have a code which is, let's say, 99% with parallelism, so we are here on the red curve, we can get with 200 cores efficiency of a speed up of 100 times. So how we can do the programming? So we have a programming model for shared and distributed memory. What you see over here is, in principle, 2 servers. Every server has its computing cores, and they are related with the memory. This situation is called shared memory model. But if we have more servers, they are connected with a network with interconnections. And there we have another model, which is a distributed memory model, because we have to access the memory on the other server and do the interchange of messages. So many computer platforms linked together by a network to build a distributed computing system is called a cluster. I have here an example of a shared memory application using the application programming interface of OpenMP. You see, after the initialization and defining that we like to have 6 threads in every programming unit, we can divide the calculation in relation to this index of this programming unit over here. This is an example, an easy example for a shared memory platform. The next we can do to treat the distributed memory platforms. There we can use the message passing interface, which is MPI. And here is a snippet of such a program code. And you see here the program starts. It gets the processing units, and it gets the processing idea. And then you can get the name of the node where it is running, and you can change the information to all the computing units which take part of this computation. I would like to make another example of a Monte Carlo simulation technique, which is also very important for high performance computing. Here's an example for the determination of the number of pi. A quarter of the area of the circle with unit radius is pi divided by 4. We can create pairs of random numbers, x and y, which are out of the interval 0 and 1, uniformly distributed. Then we can define a variable which calculates the distance and ask if this is minor or equal to 1. If it's bigger or equal to 1, it doesn't remains to the quarter of the circle, so it should be rejected. And we get an approximation for the number pi if we calculate 4 times number of counted pairs which are inside the circle divided by the number of executed. Here is a snippet which make this calculation, and here you see the result. If you have n of 10 to the minus 10 to the 7, we get an approximation for pi for 3.14. The conclusion, planning an experiment is related to creating a proposal with the experimental setup and showing with simulation techniques the sensitivity to the desired effect, which is computing intensive. No? To get the most out of computing in less time, you have to think of parallel algorithms, and you have to think of performance while implementing the code. This offers the possibility to get answers to questions in reasonable time and to treat complex problems. Thank you very much for your attention.
Okay, thank you. Questions, perguntas?